Hello everybody. In this tutorial I want to discuss with you how we can perform what is called a one-way ANOVA or a single factor ANOVA, and we are going to do also a post hoc test. So what is it that I'm talking about? Let's have a look. We have an experiment where we test two different drugs. We test the effect of these two different drugs on the concentration of a metabolite of our cells, and of course, as good scientists, we also have a control that is sort of a mock treatment where we treat the cells in exactly the same way but just without the drug. And we want to know whether there is a difference between the drug and also whether the drugs are different to the control. Now, so far so good. We have done a simple t-test where we looked at, for example, the difference between a drug and a control. But what is it? How do we proceed when we have not two samples but three samples? And in this case, we can't just simply do a t-test because a t-test only compares two samples with each other. And that's where a one-way ANOVA comes in very handy. ANOVA stands for analysis of variance, but what it does is actually it compares the means of all three samples here, and we can have as many samples as we like. It's just three in this case makes it easier. So the first thing that we are going to do is we are looking at the sample means of our metabolites. So in Excel we can do that quite easily. So here it would be equals the average of the concentration. So we do that here, and we get an average of 0.18 millimolar, and we get this for this one here as well. And here again we calculate the average for the control, and you probably noticed that we don't have the same sample size for the control. And we've got 0.5, and this, of course, control should be with an R. Okay, so here we've got our means. Let's put them right. And now the big question is, okay, we see that the mean of the samples treated with drug A and the means of the samples treated with drug B, they are not too far away. We have the mean of the control as well. And the question is there now a difference between the means? And that is actually where this ANOVA comes into place. So let's formulate a null hypothesis. And the null hypothesis for an ANOVA is, for an ANOVA, we need to say the null hypothesis that the population mean from which the sample 1 is taken, so that's our sample 1 here, and this sample that we have here represents a population, and the population mean of that sample is the same as the population mean 2 is the same as the population mean 3. And any differences that we see here in our samples is just simply due to sampling error, but not to the effect of the drug compared to the control. So our alternative hypothesis would be that at least one of the proposed population means and I write it as this mu here for the population mean, is different to the others. So that is our null hypothesis. And we set a significance level of alpha. We set this to 0.05, which is 5%. And of course, this ties in with a 95% confidence interval that we can calculate. So now what we can do is we can try to do this in Excel. So we go to the Data tab, go to Data Analysis, and here we go for ANOVA single factor. Okay, so let's delete what we've got here. And let's take this away. So how do we do that? All we need to do is we need to go for the input range. And here we take with the labels, we take the whole array of our data that we have. We are grouped by columns because we've got drug A in the first column, drug B in the second, and control in the third column. We've got labels in our rows, and we want an alpha of 0.05. And all we need to do is we choose an output range. Let's put the output here and click OK. So now we get a summary of the data that we looked at. So here we've got drug A. We've got 9 observations. For the control, we only have 8. So it's always good to check the number of counts that we have here of observations. We've got the averages, and the averages actually tie in with what we have calculated, so that's quite good. And now we are looking actually for a p-value, because if the p-value is smaller than alpha, so for p, if the p-value is smaller than alpha, it means it is unlikely that we observe this, our data, with the null hypothesis. So we would H0, we would reject the null hypothesis. So let's have a look at what the p-value is. And what we see here, the p-value, that's this value here. This p-value is very, very small. So p-value is much smaller than alpha. So indeed, we reject the null hypothesis and we say at least one of the proposed population means is different to the others. So we know that there is a difference between drug A, drug B, and the control. And we now need to find out which one it is. So what we are doing now is we can do a pairwise comparison between the means. And when we say pairwise comparison, then we can use t-tests. But there's a little twist to it. So let's create a sort of a matrix where we have drug A, drug B, and control, and we compare them. Here, drug A, drug B, and control. And we carry out t-tests. Make this a little bit nicer. So we carry out individual t-tests. So drug A and drug A, we don't need to compare that. Let's compare drug A with drug B. So we use t-test and we compare this sample with this sample. We take a two-tailed test, so that's why I put a 2, and we work on the assumption that we have unequal variances, which we can see here with the variances. We know that we have unequal variances, so that would be 3. And for the specialists, this is a Welch test. So we close that. So we have a p-value of 0.056. Let's not worry too much about the p-value at the moment, because there is a twist to that. Now we compare drug A with the control, equals T. And we do exactly the same thing. We compare A with the control. We do a two-tailed and different variances. We get a very low p-value for that. Now, we don't need to compare drug B with drug A because we've done that. We don't need to compare drug B with drug B because that would give us just 1. So all we need to do is drug B with control. Let's do that. Equals t-test again. And we need to compare drug B with control. And we do a two-tailed and unequal variances, and we get again a very low p-value. Now, we have done all possible combinations, and the number of combinations that we have to do, that actually plays a role. The number of combinations, so number of combinations of t-tests. This is given by a simple equation. The number of combinations that we do is n times n minus 1 divided by 2. And n in this case stands for the number of different treatments. So in our case, our n would be 3 because we've got 3 different treatments, namely drug A, drug B, and the control. So this is n equals 3. So we can easily calculate that. For n equals 3, we have 3 times n minus 1, that is 3 minus 1, divided by 2, and that would give us a total of 3 different t-tests. And what we are now doing is we adjust our alpha. We adjust alpha so that it takes care of takes care of the fact, my pen stopped, so it takes care of the fact that we have actually 3 different t-tests. Okay, so this is what we are going to do, is called the Bonferroni correction. Bonferroni correction. And it is very simple to do, because all we need to do is we set a new alpha, at which we evaluate the t-test. To evaluate the 3 t-tests. And this is pretty easy. What we need to do is we just take our new alpha, equals the sort of the old alpha, and divide it by the number of t-tests. By the combination of the different t-tests that we could do. And it is irrespective of whether we are just doing 1 or 2, we could do, in this case, 3, and therefore we divide our alpha by the potential number of the t-tests that we need to do. So we had our previous alpha was 0.05 and we divided by 3. So our new alpha at which we look at for our t-tests is now 0.0167. And we now compare our values for the t-tests that we got when we did the pairwise comparison with no longer the alpha of 0.05, we now use 0.0167. So we now say if p is smaller than alpha, that's the alpha nu, so if p is smaller than 0.0167, then we reject the null hypothesis. So what have we got? We've got comparison between drug A and drug B. We have a p-value of 0.056. And that is certainly larger than 0.016. So this one here, there is no difference between, so we can say no difference between A and B. So both drugs will lead to the same reduction in the metabolite. Now let's look at the difference between A and the control. We see here our p-value is certainly smaller than 0.0167. So this means difference between A and control. So we know that there is a statistically significant difference between the drug A and the control. And if we look at the difference between drug B and control, again we see a lower p-value than the 0.0167, that's the Bonferroni corrected alpha. So we can say we also see a difference between drug B and control. So what we can tell from this is that there is no difference between the two drugs, but both drugs are different from the control. And that is basically what this one-way ANOVA, one-factor ANOVA tells us when we do this correction and when we then carry out this pairwise t-tests, and that helps us to identify which one is different. Now, sometimes people don't even bother with doing the ANOVA because they say, well, if I have to do the t-tests anyway, I just do them, not bother faffing around with the ANOVA. But especially when you have got several groups to compare, the ANOVA is quite useful because you don't have to do these t-tests if you find out that all the means are the same. So I would always suggest do the ANOVA first. It is not terribly demanding. And if you find that your p-value is smaller than your set alpha value, if you find this, then you need to do the pairwise comparison with the t-tests and with the Bonferroni correction, where in the Bonferroni correction you calculate a new alpha just simply by dividing the old alpha by the number of different t-tests that you perform, and this number is given by this equation n times n minus 1 divided by 2, where this n denotes the treatments. So I hope this makes sense, and thank you very much for watching.